All right, so the exam revisions are due tonight, right? So 11:59, so if you haven't done those yet, make sure to get those turned in if you want to. So I did, just this morning, I did upload the iClicker scores again. So I did notice that there was probably about 50 more people that had their registration straightened out now. So check that. Okay, let's quiet down. Check that and make sure your points are up. If not, then you still have to take care of that, right? If you want to apply those points. Okay, so we are in chapter 23. We have been looking at reactions at the alpha position of ketones and aldehydes. And we so far have looked at the formation of enols and enolates, and we've looked at then really the first reaction is the halogenation at that alpha position. Okay, we looked at the halogenation under two different types of conditions, under acidic or basic conditions. All right, we can use either of those conditions. All right, so what we're going to do today is look at our second reaction at the alpha position, and this is going to be an alkylation reaction. So we're going to be adding an alkyl group at that position. So all we're really doing is just a substitution reaction with an alkyl halide, right? You learned those back in 2310 last semester, right? Substitution reactions of alkyl halides. The only difference here really is that we are using an enolate as the nucleophile. Okay, so we didn't know about enolates at that point. Okay, after that, if we get there today, we are going to start into it's not really a different reaction, but there is a different part of it. And so the different part is called this decarboxylation step. And these are going to be reactions of beta dicarbonyls. Okay, and there's going to be this extra step to it. All right, any questions about where we're at, what we're doing? All right, let's do our clicker. All right, so here we are down here. Predict the products, write the mechanisms for the alkylation reaction. Okay, so here's a couple of examples. We are using, in these cases, is the most common is this base that we talked about is called LDA. Right, so this stands for lithium diisopropylamide. So lithium plus. And this amide part, remember, it's like an amide, but it's just the nitrogen part, I guess, diisopropyl. So this nitrogen has two non-bonding pairs of electrons and a minus charge. Okay, so it's really this part that's acting as a very strong base. And the other key thing about this strong base is that it's bulky. Okay, and remember that is important because it inhibits or reduces the ability of the nitrogen of the base to act as a nucleophile. Okay, so it's only going to act as a base, remove a proton. It's not going to attack the carbonyl carbon. Okay? We showed, I think yesterday, how to make this LDA, right? Did we talk about that? No, maybe we didn't. Okay, so oftentimes you make this base kind of in situ, in the flask, okay, before you use it. And so you just start with diisopropylamine, and all we do is deprotonate this. And so commonly we use butyl lithium. Okay, remember, so it's an organolithium, super strong base, can easily deprotonate this to completion. So the equilibrium would lie very much to the product side here. Plus, what would be our other product? Oops. Dang, I can't. I've got a different stylus today, and it's a little tricky to find the point. What would be the other product? Just butane, right? All right, so why don't we just use butyllithium if it's such a strong base? Why don't we just use butyllithium as the base? It's not bulky, exactly, and it will attack the carbonyl carbon, right? We looked at the reactions of organolithiums or organometallics with carbonyls already, right? Some chapters ago. And so we know that an organolithium would attack a ketone to form a tertiary alcohol, okay? All right, so what we're going to do, first step here, we could draw out this base. We got the minus here. This is just going to remove one of the alpha protons. All right, so this is going to go here. And these electrons, I'm going to go over to the oxygen. Well, we can draw both resonance structures. So we're going to draw the intermediate here, the enolate intermediate. I'm just drawing this one, and we have an H still here. And so remember, this is in equilibrium. Not equilibrium, that's dumb. It's in resonance, right? Dang. I'd subtract a lot of points from myself for saying that. All right, so this is the resonance structure, right? So we know that those electrons are simply shared between the oxygen and the carbon. So this is actually what they call a bidentate nucleophile, right? So it could actually react at either the oxygen or the carbon end of this, all right? It tends to, in these types of reactions, to react at the carbon, okay? Because like I mentioned before, because the oxygen is more electronegative, it can better hold the minus charge. That means the carbon can't hold the minus charge as well, and so that actually makes it more basic and a better nucleophile. Okay, so we'll almost always, there's only a few scenarios where you can react something up on the oxygen. Okay, and so we can draw this like this. Those electrons go there. Oops, I didn't even draw my, couldn't see where my arrow was supposed to go because I didn't draw this in here yet. Okay, so this is going to attack here. These electrons are going to go onto the iodide. So this is just simply an SN2 substitution. Okay, so our product is just going to now have, it still has one H here, and we've added a methyl group to the alpha position. Okay? So in these reactions, sometimes it can be kind of tricky. You might ask yourself now, I know somebody is asking in their head the question, okay, we added one methyl group, can we add another? Can we add another, right? How many could you add here? And so it is true that it can be a little tricky on the stoichiometry of how much, the enolate, the amount of base to the ketone to form the enolate, and how much of the electrophile you add. It can even matter which order that you add things. Okay, am I going to form the enolate and add the methyl iodide to that, or am I going to have a solution of methyl iodide and add the ketone to that? So sometimes the order of addition or the direction of the addition is important, and you know, you have to play around with those things sometimes, okay? So we should be able to add one of these onto one of those carbons. Okay, so here's another example. So just see if you can draw the product for that second reaction. Usually these reactions are done quite cold too, at like minus 78 degrees. Minus 78 degrees Celsius. Okay? So all we're going to do here, we're going to draw out our ketone, and we're going to add this whole group here, this whole group that's attached to the halogen, to the alpha position. Like this. All right? Okay, so that's the simple alkylation. What if we want to do an alkylation on a ketone like this? All right, so an unsymmetrical ketone. So when we think about this first step, we're going to use some kind of a base to form an enolate. But how many different enolates could we form from this ketone? Just one? Two, right? We could form an enolate to either side. So we could form an enolate that would go to this side, or the enolate to the other side. To the other side. Right? And these are both going to give different products, right? If we add our iodoethane to this one, we draw our arrows like this, and like this. And we would have added, draw this, let's see. Our other ethyl group over here, if we did the same reaction over here, it would add at the other alpha position, and that would give us this product. Okay? So, it'd be nice to be able to control which side we could do this at. Yeah, question?
So for symmetrical structures, if we had two equivalents of the alkyl group, could we add one to each alpha carbon?
Okay, so the question is, could we do this twice? Could we add it to well, the question would partly be, could you add it to, if you did it twice, say if we have cyclohexanone, and we added it twice, so we've seen already that we could go from here, so this kind of is relevant to this example that I have up here. If we added a methyl group, like we did on the last slide, and say we got to here. You know, can we do this reaction again, right? And if we can, which side is the second methyl group going to go to, right? Are we going to get, so this is exactly the question that we're asking here. Are we going to get both of the methyl groups on opposite carbons, or really, are we going to get both methyl groups on the same carbon. Okay? So this has to do with the enolate. All right? So if we can control which enolate we form, then we can control where the alkyl group will go. All right? So let's take a look at these two enolates that I've drawn up there. And let's ask ourselves if we think one of those enolates would be more stable than the other. Which one would be more stable? The one on the left, right? And why? Because the alkene is more highly substituted, right? So this one is actually more stable. All right, so if we can form that under conditions where the more stable product is formed, or the more stable intermediate is formed, then we could selectively make that enolate. So what kind of conditions would we call that when we're just going to form the more stable one? Thermodynamic control, right? So this would be formed under thermodynamic control. Okay, Is there a question up there?
Yeah, from the previous slide, what's the function of THF?
Oh, THF, do you remember what THF is? Okay, so THF is this molecule here, tetrahydrofuran. So this is just a solvent. Okay, and these reactions are a little tricky too because you need to have a solvent that can dissolve both the neutral compounds at the beginning and the ions that are formed in the middle. Usually butyl lithium, you can buy it as a solution, usually comes in a hexane solution. All right, but if you just run the reaction in hexane, then the ketone might dissolve, but once you deprotonate it and form this enolate anion, it just precipitates out of solution because the ions can't dissolve in hexane. Okay, so we use THF as a common solvent that adds some polarity and some ability to coordinate those cations.
Okay.
Yep, good question. All right, so this one over here we said is more stable. The one on the right is formed faster, okay? Because you can imagine that the methyl group on the side, the hydrogens on that alpha position are more exposed, are easier to get to, all right? So they're removed faster, okay? So we would call this one the kinetic enolate. We keep seeing this same kind of thing, don't we? Okay, because this position over here is more exposed. It's easier for a base to react there very quickly. Okay? So, if we can run this reaction under conditions to control whether we're getting thermodynamic control or kinetic control, then we can control which enolate we form and which product we form.
So,
Yeah.
like the base promoted alpha halogenation, can we get it to go all the way to remove all of the protons from both of those alpha carbons?
So the question is, again, can we do this over and over again? I think what we would probably do is do the reaction sequentially. So we'd add one alkyl group, we'd isolate our product. We'd do it again, and we'd do it, instead of just mixing it all together and having it go 4 times or 2 times, I think we'd have to, and I think what I would like us to do in here is to consider those as additional reactions, okay? But there's no reason why you couldn't do it several times like that, okay? But let's do it once at a time instead of trying to do it all at once, okay? All right, so let's think about how we might do this reaction under kinetic control. Okay, so what we want is we want a very reactive base that will just snatch off the most accessible proton as fast as it can and just kind of irreversibly give us an enolate. All right, so what kind of a base do you think would be good at doing that? A big, strong, bulky base. And that, here, I'm not going to draw it all out here. That is just what LDA is. Okay, it's one bulky base. Okay, so in this condition, this enolate formation is essentially irreversible. It's going to be one-dimensional because the base is so strong, the equilibrium is just going to lie on one side. Okay? And so we're going to form this. And we're going to say that this is essentially irreversible. All right, so then if we add our step 2, we add our ethyl iodide to this, it's just going to react at this less substituted side. Okay. So what is it that we have to usually do differently if we want to get a thermodynamic product or intermediate? Usually we want it warmer, right? So temperature can be an issue, but what do we want to happen? What's different as far as the mechanism, not just temperature? What does a warmer temperature allow to happen? Reversibility, okay? So what we want is to use a base or a scenario that allows the enolate formation to be reversible. Because the less exposed position is always going to be the fastest to be removed, okay? But once it's formed, if it can go backwards and equilibrate, then the more stable one will predominate, okay? So we want this step, this first step, let's just cross this out, we'll put it in afterwards. We want this step to be reversible. Okay, so what we're going to do is we're going to use a base that also, and a solvent system that has a proton source. Because we want to deprotonate and we want to reprotonate. Deprotonate, reprotonate. We want to have an equilibration going on here. Okay, so oftentimes what's used is some type of a bulky base is common. I don't know if it's always required, and it would be something like maybe tert butoxide in tert butanol. Okay, so remember, whenever we use these alkoxides as bases, we typically use them in their conjugate acid as a solvent, all right? Because then when the proton goes on and off, it gives always the same thing, okay? And so this will allow equilibration because we can form the faster forming enolate, but it can reprotonate from the alcohol, okay? And so this reaction may not go, it's not, well, we don't want it to be irreversible, right? So this one is going to just equilibrate, giving us the more stable enolate. There is a way that you can actually run this reaction under thermodynamic control, even using a strong base like LDA. All right, anybody have an idea how you might be able to do that? Okay, so the way you would do that is so typically if we want to run the reaction like we're doing up on the top, we would add to our flask some diisopropylamine, Okay, cool it down to minus 78 in our dry ice acetone bath. We would add butyllithium to that and let it stir a little bit, and it would deprotonate and it would form LDA. Okay? So then, usually what we would do is then drip in the ketone into the base. And so there's an excess of base at all time. It irreversibly deprotonates the alpha position to form the enolate, but it's in a very basic solution. There's no proton sources around, and so it just forms and it's irreversible. However, if we reverse the order of that, if we make our LDA and we drip that into the ketone, so we just reverse how we do it, then we always have an excess of ketone. And so then we deprotonate, but then another ketone molecule can act as the proton source. So we have different enolates forming back and forth, and that allows it to equilibrate. Okay, so that's kind of just another tricky way to do it. But we'll just remember we can use most of these. I think on one example I actually use methoxide and methanol, but when we oftentimes do this by using an alkoxide with a alcohol. Okay, that provides the proton source that allows equilibration. Okay, and then we add our alkyl iodide, and now the second one will go to the more substituted side. So we get a methyl and an ethyl at this position. Okay? Okay, so we can also do alkylations of other carboxylic acid derivatives. Okay, so these are just some examples where in the top one we're doing it for an ester. So we can form an ester enolate. Okay, so the first step would form the enolate of the ester. So of course it only has one alpha position. Come on. And so when it then reacts, I'm going to turn this around. So the other thing I didn't really bring up, so I've been drawing, some different examples of alkyl halides here. So what do you think? Are there any limitations on the type of alkyl halide that we can use for this reaction? Well, the chloride we could use, huh? Fluoride, yeah, fluoride probably wouldn't work. But what about the structure of the alkyl part? Yeah, so it's probably mostly has to be, it's going to be best, let me think of what I'm doing here. It's best if it's methyl or primary, right? Because essentially we're doing an SN2 substitution on the alkyl halide. And that goes faster if the alkyl halide is less substituted, okay? You might, I don't know, there might be some examples where secondary might work, okay? But mostly, let's say mostly Rx should equal either methyl X or primary. Okay, if we get secondary or tertiary, what would happen if we formed this enolate and then we added a tertiary alkyl halide? Just nothing? Or would something happen? Something, right? Okay. Good answer. So what kind of something would happen? What happens when we take a tertiary alkyl halide and we add a strong base to it? An elimination reaction, right? An E2 elimination reaction. Remember that stuff way back last semester? Okay, So we could have various bases, right? An enolate, it could just be another base that triggers a elimination of a tertiary alkyl halide. Okay? All right, so the bottom one, we can also form an enolate of a nitrile. So the LDA would remove one of these protons, alpha to the nitrile. I'm just going to draw it like this. I don't think we've actually drawn out an enolate of an, oops, I did that backwards, of a nitrile yet. Okay, so we would have this with the anion here, and this anion also has resonance, right? Just like the other ones, where these electrons could move here, and these electrons could move over onto the nitrogen. And so the resonance would look like this. So we'd only have a double bond to the nitrogen. We'd have a double bond over to here. And now we have two non-bonding pairs on the nitrogen, so the minus charge is shared with the nitrogen. Okay, in our second step, we're using here benzyl bromide. So these electrons are going to go here and displace this, or we could draw it from this resonance. They'd go here to reform the nitrile and then attack like that. And so I did the same thing again. And so we added this benzyl group. Okay? All right. What time is it? Oh, we got time. Okay, so here's just a few examples. All right? So take a couple minutes, see if you can draw the products of these reactions. All right, so on the first one, we're using LDA. And so is that going to form the enolate to the less substituted or the more substituted side? Less substituted side. This is how we make the kinetic enolate. And so our benzyl group here is going to end up on the less substituted side. We have this ethyl group over here already. And our benzyl group, I had to just make a little benzyl group there, would go on to that side, okay, less substituted side. All right, what about the second one? We're using sodium methoxide and methanol. Is that going to form the more substituted or less substituted enolate? The thermodynamic more substituted enolate. Okay, so our product, all we're doing is adding a methyl group this time. The methyl group would be at the more substituted alpha position. All right, The next one, we can't really have a thermodynamic or kinetic, but we're just going to end up with this propyl group at the alpha position. So it's going to be right here. Okay? And then the last one, right? So this is a beta dicarbonyl. And remember, the position between the two carbonyls is by far the most acidic. Okay? It was much more acidic even than water. All right, so we're using sodium methoxide. Notice that in this reaction, what I'm doing is I'm using methoxide and methanol, which matches the ester group. Okay, and why would I do that?
So you don't have a competing reaction of transesterification.
Exactly, because we can do transesterification reactions as well. If I used ethoxide, then we might get a mixture of methyl esters and ethyl esters in the product. Okay, so now if that competing reaction is taking place, if we just don't, it doesn't cause any changes. Okay? All right, so we're going to just add our methyl group onto the center carbon here. I'll know this out. And then we're going to see this reaction coming up in a minute. And this is another place where we could do another reaction, add another alkyl group at the middle position if we wanted as well. Okay? Yeah, question?
So would it have mattered on the last one if you used LDA?
On the very last one?
Would it still do that?
Yeah, it would still do that. And in fact, what you can do if you use something like LDA, you can also, if you use two, what do you think is going to happen if we use two equivalents of LDA? Okay, it can form, if we use two equivalents of LDA, it can form a dianion, kind of a dienolate that looks like this. Okay, and then we have two possible positions for the reaction to take place. Either this position or this position over here. Okay, so which one of those two positions do you think would be more basic or more nucleophilic? The which? The one on the end, because that's the least acidic proton, and so that's the most basic position. Okay, so this position is the most basic. And so it would also be most nucleophilic. So you could even alkylate off that N carbon if there are reactions like that. Okay? All right, so let's just look. This is kind of a different thing that we want to consider. So I don't really have any alkyl halide in this. If we had this ketone and we just mixed it with sodium methoxide in methanol, what do you think would happen? Would we get any change in the compound at all? Yeah, so that's the thing, is we're starting out, notice that this molecule has a chiral center in it, all right? And so this has a stereogenic center. And so if we form the enolate, let's just draw out the enolate, right? And we're doing it under thermodynamic conditions. We form an enolate like this, and once we've done that, we've lost our stereochemistry. All right, and then if this reacts with the methanol from there, it can protonate either on the top or protonate on the bottom, okay? Because that enolate is flat, right? So it can come in from the top. And if the H comes in from the top, the methyl group would be going back. Or if the H comes in from the bottom, then essentially we get what we started with. Right? Because then the methyl group is up and the H is back. So we end up with a racemic mixture. So do you think this process here, this loss or this racemization of that ketone can happen under acidic conditions as well? So what about, if we add just some acid, let's say acid and water or something. Okay, what kind of process for a ketone or with an alpha position can acid catalyze? Protonation of the oxygen, and then what forms? What it can form an enol, right? Because acid catalyzes enol formation. And if you form an enol to that side, likewise you lose the stereochemistry. Okay, so this could also cause this to become racemic, and it would happen, say, let's just say via the enol rather than the enolate. Okay, so it's just something you have to keep in mind if you were doing this kind of chemistry. Okay, so that's all of the alkylation reactions. So I have one more slide here, but let's just skip it for today. Remember to get those exams, the revised ones, all submitted if you haven't yet. And I will see you guys on Monday.